Continuing with groups on the periodic table. You're probably thinking this is going to take forever. Good Lord, the last video, we got through groups 1 and 2. I got 18 groups. Oh, this isn't so bad. We're going to lump groups 3 through 12 together and call them the transition metals. Now, if you look at this group on the periodic table, it might look familiar to you. We've previously called this the D block. These are the elements that fill D orbitals. Now, technically, the F block at the bottom of the periodic table, those elements have been pulled out for a few reasons. Yeah, they do fill the F orbitals as well as the D's. And they do have some kind of unique properties. These are mostly your synthetic radioactive elements. They're called the lanthanides and the actinides. Technically, they do kind of fall into this middle transition metal group. If you look at atomic numbers, atomic number 57, lanthanum, is technically in the D block. If you go to 58, cerium, that's kind of pulled out to the bottom in the F block. It is considered part of the transition metal group. Same thing with the actinides. Numbers 90 through 103, we're still going to call them part of the transition metal group. Now, in general, this is where you find your typical metals. And let's just put that, their properties. Typical metals. When you ask me to think about a metal, these are the elements that I think about. Manganese, chromium, mercury, copper, iron, zinc. They're ductile and malleable. They have luster. They have high melting and boiling points. They're great conductors of heat and electricity. When you ask me to think of a metal, I think about transition metals. Often. The lanthanides and actinides, and again, we've mentioned that they're pulled out, and often they're called the rare earth metals. More specifically, in general, we can just make note they're unstable. Many of them are radioactive. And again, radioactive means unstable nuclei. These are some big elements down at the bottom of the periodic table. When you get that many positive protons all together, it's hard for there not to be some degree of repulsion in that nucleus. Radioactive and unstable, those kind of go right together. We can also make note that some of them are synthetic. These are some of those elements that were discovered through nuclear fusion experiments. They're interesting. However, we do not have any samples that I can show you in class, but I can show you lots of examples of these general transition metals. We don't have any rare earth metals. Now, the other thing that we should mention, why are they called transition metals? To me, transition means like some kind of a change. It's because the number of valence electrons can change. So when I think of transition, I think of a change. It's because of these orbitals that they're filling. We're filling high energy, unstable d orbitals. The electrons in these orbitals, on occasion, tend to move. And so sometimes it's hard to really say, there's 3 valence electrons, there's 2 valence electrons. We may not know at any given point in time exactly how many valence electrons are in that outer shell. That's why they're called transition metals. All right, there. Groups 3 through 12, done. We're cruising. It gets even better. Watch this. Let's go over to groups 13 through 16. Now we're in the P block of the periodic table. And often it's called the main block. These are main block elements. So you've got the carbon family, the boron family, carbon family, nitrogen family, oxygen family. They're not given fancy names. It's really just called the carbon family. It's all the elements in the group carbon and down. These are often stable elements. Like carbon is very stable. Going down, you have carbon, silicon, germanium, tin, lead. These are all elements that we can look at in class. Describe the groups of the main block. Well, here's one trend. Let's look at the trend in valence electrons. If I write these electron configurations, these elements aren't super crazy. Let's go boron. Number 5. 1s2, 2s2, 2p1. We're just starting to fill the P block. Let's go across to carbon. 1s2, 2s2, 2p2. Nitrogen. 1s2, 2s2, 2p3. And oxygen. 2s2, 2p4. Alright, so we're just starting to fill the P block. And obviously elements like aluminum, silicon, phosphorus, sulfur, they'll follow similar trends. Valence electrons are all the electrons in the highest energy level. The highest energy level occupied is the second. So we're looking for all the electrons in the second energy level. Two s2, 2p1. There's a total of 3. Everybody in the boron family will have 3 valence electrons. The carbon family, all the electrons in the highest energy level, 2 in the S, 2 in the P, 4. Nitrogen, 2 in the S, 3 in the P, 5 valence electrons. The oxygen family has 6. Those are all valence electrons. As you go across, each group just adds one more electron to that highest p orbital. So our valence electrons just increase by 1. Now again, you could write these as the noble gas shortcuts. The noble gas shortcut, let's say I do my friend boron. Boron, I would shorten this up, helium. And then I say 2s2, 2p1. Now sometimes the biggest problem that I'll see with these electron configurations, and the question says, how many valence electrons? Valence electrons are all the electrons in the highest energy level. The highest energy level is the second. It's all the electrons in the second energy level. 3. These are your valence electrons. The inner core electrons are what we can shorten up by doing the noble gas shortcut. So this 1s2, that was the core electrons, which we can represent here with helium. it's not the highest energy orbital. So by accident, sometimes the question will say, how many valence electrons? People will say 1. Because they'll look at the electron configuration and they're only looking at the last orbital. Well, that might be the highest energy orbital, but valence electrons are in the highest energy level. So we want all of the electrons in the second energy level, regardless of orbital. Are they in the S, the P? We're going to add them all up. As we go across to oxygen, again, I could shorten this up and say oxygen is helium, and then I'd say 2s2, 2p4. I'm shortening up the core electrons by saying helium. These 6 are all my valence electrons, not 4. And of course, if it's multiple choice, 4 is going to be one of the choices. Valence electrons, electrons in the highest energy level, not the highest energy orbital. Now again, this pattern of valence electrons, it'll follow down the entire group. So example for the carbon family. Carbons, let's do a shortcut. Carbon's shortcut would be helium, and then we could say 2s2, 2p2. Now let's go down the group. Silicone. If I do silicone, its previous noble gas would be neon, and then I'd have 3s2, 3p2, and so on. You're figuring this out. Germanium. I go backwards to argon. 4s. Oh, this is a good one. Okay, 4s2. Now I have to go 3d10, and then I go back to the 4p for 2. So the whole electron configuration thing, that doesn't just drop to the wayside. We're going to use this all year. When we get into bonding and chemical reactions, it's about the electron structure. Specifically, the valence electrons. The electrons in the highest energy level. So now let's look at valence electrons for the carbon family. 4. The highest energy level is the second, 2 in the S, 2 in the P. Silicone. Valence electrons. It's still 4. We're just in a higher energy level, but that energy level still has 4 valence electrons. Now look at argon. The highest energy level occupied by electrons is the 4th. So we want all the electrons in that highest 4th energy level. There are still 4 valence electrons. The D's, even though they get filled kind of out of order, they're not considered valence electrons. They're in the inner energy level, the 3rd energy level, and they really would not be involved in bonding or a chemical reaction. It would be the electrons on the outside, the outermost valence electrons. There are still 4. So this trend with valence electrons, it'll follow down the entire group. They'll all have 4 in their highest energy level. Oh, let's see here. Which 2 main block elements represent the 2 most abundant elements of the Earth? I mean, there's a lot of abundant elements. There are very common elements that will fall into this main block. I don't know if you want to argue for 2. I'd maybe definitely say carbon. We could put, let's put oxygen. That's a Y. Silicone is one of the most abundant elements in the Earth. We could even put nitrogen down. Nitrogen is one of the most abundant elements in air. I don't know if we're considering in the Earth or in our atmosphere as well. I mean, this main block is where you find the building blocks of organic chemistry, carbon, hydrogen, oxygen, the building blocks of life. Super abundant, common, stable elements in this main block. And it's very important to understand some of their trends, especially with valence electrons. One other thing that's kind of interesting, especially like the carbon family. The carbon family will start with, obviously, carbon. Carbon is a non-metal. I guess you can kind of see that, non-metal. Then, here's where you start finding your metalloids as well. That staircase, if it's written on your periodic table, kind of cuts through the middle of this main block. Silicon and germanium are both metalloids. They fall along that staircase of having properties similar to both metals and non-metals. We'll look at some silicon in the lab. Then finally you get down to the way bottom of this group and you will find metals. Tin and lead are very metallic. That's kind of an interesting little tidbit. When you get into this area of the periodic table, you will start finding groups that have different types of elements. But they'll be very similar when it comes to chemical reactions and bonding, because their electron structures will still be very similar. Same amount of valence electrons.